When it comes to the fundamental forces of nature, there's one that we experience every single day, but have a hard time explaining: gravity. We know how it works in a broad sense, thanks to Einstein's theories of general relativity. But as far as how it works in the universe on a larger scale, that's still a bit of a mystery. There are lots of theories attempting to explain gravity, and one of them proposes that what we feel as gravity is not really a force at all, but a side effect of something else entirely. In fact, this idea has some serious scientific backing, and if it turns out to be true, it could revolutionize our understanding of the universe, and many physicists are happy with that. But there are some problems with Einstein's idea. Like, for example, trying to mesh it with quantum mechanics. One of the most successful theories ever developed, quantum mechanics, explains how matter behaves at the atomic and subatomic level. But so far, physicists haven't been able to develop a quantum theory of gravity. That's because, as we said before, gravity is extremely weak, which would make gravitons extremely difficult to spot. This interaction would exchange a different type of particle that has mass, like a hypothetical particle called a Dalton. Daltons would mediate a force that's similar to gravity, but not exactly the same. Now, while we don't have direct evidence for either of these ideas, there are a few indirect hints that they might be right. But in 2018, researchers found similar discrepancies in other experiments, hinting that there really might be something going on. But the jury is still out on whether these hints point to a modification of Einstein's theory or something else. For example, in 2014, researchers found that the results of certain particle physics experiments did unmatch up with predictions based on Einstein's theory of general relativity. Some physicists think it's unlikely because even if it's true, the effects of such a modification would likely be too subtle for current or even next-generation experiments to pick up. You just have to look at all those crazy quantum foams out there. It's hard to believe that a force as simple as gravity could arise from such a cacophony of activity. But then again, that's why they call it the fundamental force. Others aren't so sure, but time and better equipment will tell. The discrepancy wasn't huge, but it did suggest that there might be some kind of new particle mediating a force similar to gravity, but not exactly the same. Then the force we call gravity would come about as a byproduct of the interaction between Daltons and normal matter. This idea resolves the issue of gravitons traveling faster than light, since Daltons wouldn't have to. And it gets rid of the mass-based gravitational anomaly at short distances by making clear that gravity becomes weaker, not infinitely strong, at very short distances. But there's another problem too. According to Einstein's equations, gravitons would have no mass, which creates a few issues. If you'd like to help us make more videos like this in the future, please consider supporting us. For one thing, if they have no mass, how do they travel? After all, nothing can travel faster than the speed of light. And gravitons would have to travel faster than light in order to mediate an instantaneous force like gravity does. Another issue is that massless gravitons would cause the force of gravity to become infinite at very short distances. That's partly because gravity is so weak compared to the other fundamental forces. A force is any interaction that, when unopposed, will change the motion of an object. But as far-fetched as these ideas may sound, they're taken seriously by many physicists. That's because in 2015, the Nobel Prize-winning physicist and former director of the Institute for Advanced Study died. Before he passed away, he asked his close friend and colleague, theoretical physicist G.A. Miller, not to open his coffin if he died. And when Polchinski passed away, Miller honored his friend's request and instead opened the top of the coffin to reveal an empty box. That was supposed to symbolize Polchinski's belief that empty space was not really empty, but filled with all kinds of particles and interactions that we currently can't detect. But that's not the only reason why we might want to come up with a new theory of gravity. As for dark matter, it makes up around 80% of the matter in the universe. But again, we have no idea what it's made of. One intriguing possibility is that both dark energy and dark matter could be explained by modifying our theory of gravity. If that's true, then Einstein's theory of general relativity is just an approximation of a more complete theory. There are also some things about our universe that Einstein's theory just can't explain, like dark energy and dark matter. In some versions of this idea, the force we call gravity is actually a result of particles exchanging another type of particle called a graviton. Gravitons would act like the other force carriers, like photons, which carry the electromagnetic force, and the gluons and W&Z bosons, which carry the strong and weak nuclear forces. All these particles are called bosons after the physicist S.N. Bose, who helped develop quantum mechanics. And they all have a counterpart called a fermion. Fermions are the particles that make up matter, like protons, neutrons, and electrons. Dark energy is the name given to a mysterious force that makes the expansion of the universe speed up over time. And dark matter is an even more mysterious substance that doesn't interact with regular matter or light, but whose gravity seems to affect entire galaxies, because it always pulled things together rather than pushing them apart like electromagnetism. That was until 1915, when Albert Einstein developed his theory of general relativity. In it, he describes gravity not as a force at all, but as a curvature in spacetime caused by mass. This means that massive objects don't exert a force on other objects. They simply cause spacetime to curve in such a way that other objects move along the curves naturally. It's kind of like if you had a bowling ball resting on a trampoline. The ball would make a dent in the trampoline, pulling the surrounding balls toward it. But the bowling ball itself isn't exerting a force on the other balls. It's just rolling downhill in response to the dip created by the trampoline. So when you walk forward, it's because you've exerted a force on the ground behind you. And the ground has exerted an equal and opposite force back on you, propelling you forward. Forces come in different varieties. For example, electromagnetism, which is the force that causes magnets to attract or repel each other, and the strong and weak nuclear forces, which govern how particles interact at the atomic level. Now, before we get into this mind-bending idea, let us make sure we re-clear on exactly what we mean by the word force, because that can be kind of confusing. Gravity, though, is a little different. While we experience gravity as a force, for centuries, scientists treated it differently from other forces, so according to general relativity, we don't need a new theory to explain how gravity works. In order to see how gravity works at the quantum level, we'd have to find a way to measure it under extreme conditions where matter is moving very fast or is squeezed into a very small space. The best current estimate is that dark energy makes up around 2/3 of the entire universe, but we know almost nothing about it except that it exists. That's where ideas like the one that gravity isn't really a force come in. But unlike those other forces, gravitons have never been detected. One way around this problem is to say that gravity isn't really a force at all, but a side effect of a more fundamental interaction. And that's not the only idea out there. There are several others that ditch Einstein's idea of massless gravitons. This view of empty space is known as quantum foam or fluctuating vacuum. And it's where those hypothetical particles, like the dilaton, that mediate a force similar to gravity, but not exactly the same, would come in. Unfortunately, later analysis showed that other factors likely accounted for the disparity. It's also worth pointing out that the data sets used in those experiments were incredibly precise, which raises the question of whether our current technology could ever be precise enough to confirm a modification of general relativity. But regardless of whether gravity turns out to be a force or not, it's safe to say that the universe is a lot more complicated than it looks. Thanks for watching this episode, which was brought to you with the help of our patrons.